Okay, Lama, let's begin after the interval, right? Okay, let's start the second session for today, right? Okay, now after studying about the ionic radius and the atomic radius, now we are heading up to the next period trend, right? Next one. Yes, now we are going to study about the ionization energy. The period trend we see when going towards right of the period, right? Of these ionization energies, right? So actually in small ages, right, in your O levels, you may have studied about the ionization energy trend. Do you remember that? No. That zigzag trend, the zigzag trend going towards right of a period, right? That is about the ionization energy, right? So we are going to study about that thing, the zigzag trend, right, along a period, the ionization energy trend, right? So basically in A levels, we are going to discuss thoroughly about the reasonings, why we observe such a trend, such a pattern going towards right of a period, right? So we are going to discuss the reasons why we would see such a pattern, right? Okay, that is the main discussion or focus in A levels, right? Okay, let's start the discussion on ionization energies, right? Right. So first of all, just quickly have an idea about the ionization energy, what it means, the ionization energy. Yes, tell me. Right. Okay. The ionization energy means, right, the minimum energy you need to supply to eject an electron from a gaseous atom. The minimum energy you need to supply to eject an electron from a gaseous atom, so that you form gaseous positive ion, right? So that is the ionization energy, right? Got the idea, no? The ionization energy is this. So as a equation, as a chemical equation, you can write, if you have to consider the first ionization energy, right, I1, right, we can write it is the minimum energy needed to supply to eject an electron from a gaseous atom to produce the gaseous plus 1 ion. So you are ejecting 1 electron. So that is the ionization energy, right? So we are going to discuss about the trends of first ionization energy along a period first, right? First we'll discuss about what will happen along a period. After that discussion, we can go towards what will happen along down a group as well, right? Okay, first discussion is about what happens to the ionization energies, first ionization energy mainly, when going towards right of a period, right? First ionization energy when going towards right of a period, right? So let's consider this as the first ionization energy, right? First ionization energy. Right, let's consider the second row elements. Let's see how it appears, the ionization trend going towards right of a second row elements, right? So what are the second row elements? Right, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine and neon, right? So we are going to discuss about the ionization trend of these guys, right? Okay, so let's come up with a graphical form. Let's come up with a graphical form. Here the ionization energy at this axis, ionization energy, in kilojoules per mole. At this axis, it is about the atomic number, right? Atomic number. Right. Let's discuss what will happen. So basically, what we know is, first thing, what we know is actually going towards left to right, the atomic radii becomes smaller, becomes smaller. From left to right, the atomic radii becomes smaller, right? You know that now. We had discussed the trend in the atomic radius now, going towards right of a period. So when the atomic radius becomes smaller gradually, the outermost electron, the electron which is to remove, the most loosely bound electron, is much closer to the nucleus here than in here. Than in here, the electron which is supposed to release is much closer to the nucleus here. So that is more attracted to the nucleus in here than in here. So the most loosely bound electron is greatly attracted to the nucleus at the neon. So to remove that electron from neon atom, you need much more energy, great energy than here, because this guy's outermost electron is very loosely bound to the nucleus, because the distance between the nucleus and the outermost shell is a bit high compared to here. So according to atomic radius, right, we expect this kind of a variation, right? That means the ionization should increase going towards right, because as the atomic radius gradually decreases, you need much great energy to eject an electron from there, because the loosely bound electron is strongly attracted to the nucleus when you are very small. So according to the atomic radius, we expect some kind of a increasement of the ionization energy, the minimum energy needed to eject an electron, right? This is according to the atomic radius. But another thing matters, right? This is what to expect, right? According to the atomic radius, right? But another thing happens. What is that? There are a few guys with some stable configurations. What are those? This one, neon, it is with, right, helium and 2s2 2p6, no? Stable configuration. The outermost shell is completely filled. With nitrogen as well, the helium with 2s2 2p3, with beryllium as well, helium's configuration with 2s2. These are referred to as stable configurations, right? When you are with a stable configuration, you are not that much keen to get rid of that configuration, right? When you are with a stable configuration, when you are stable with the electronic configuration, you are not keen to become unstable, no, by releasing that configuration, by changing that configuration, right? You then try to stay with that configuration and not trying to release electrons out from you when you have a stable configuration, right? So that is what happens to the beryllium, nitrogen and fluorine. So we need to supply some great energy than the expected by the atomic radius for these three guys. Why is that? Because those are not keen to eject an electron from those stable configurations. So when it comes to beryllium, the second atom, we need much more higher energy than the expected, because beryllium is not keen to release an electron from that stable configuration. So the beryllium's value appears not here at here. When it comes to nitrogen, the same. For nitrogen as well, you need to supply much greater energy to get that electron from nitrogen, right? For the neon as well, because those are with stable configuration. So the nitrogen's value is not appearing here, but here we need to supply bit great energy to eject an electron from nitrogen than the expected by the atomic radius, the neon's value is also like that. Right? So they are the beryllium, nitrogen and argon appears. So neon appears, sorry. Right now? So those with some stable configurations, right? Those with some stable configurations. Right? So this guy is with helium and 2s2. This is with helium and 2s2 2p3. This is with, right, so I write the configuration in black color, no? So for the clearness, right? Helium and 2s2. This is helium and 2s2 2p3. This is with some helium and 2s2 2p6. Right now? So due to the stable configurations, you would need to supply but bit greater energy than the expected by the atomic radius, right? And then some elements are there, those will release their outermost or most bound electron more keenly, as they can achieve the noble gas configuration, or they can achieve some stable configuration by releasing so. So the opposite of these guys are not keen to release an electron because they will get rid of that configuration, the stable configuration. But some elements are there, by releasing one electron, they can come up with a stable configuration. Such elements release that electron more keenly with lesser energy than the expected by the atomic radius. What are those? One is actually the lithium. Lithium, by releasing the electron, lithium can achieve the noble gas configuration. By releasing the electron, lithium can come up with the helium's noble gas configuration. So lithium's value will appear here, bit lower than the expected. Right? Lithium. Then this one, carbon, sorry, the boron, that one, right? The boron. By releasing one electron, it can come up with the beryllium's configuration. So electron will be released keenly, the boron. Right? So lithium, boron, as well as the oxygen. By releasing the electron, it can come up with the nitrogen's stable configuration. So oxygen as well releases the electron more keenly. So less energy needed. See? Like this. Oxygen. So this gives you the zigzag variation. This gives you the zigzag variation. If you are to match these things, see? This gives you the zigzag variation, see? That is your zigzag. That is your zigzag. Lithium, beryllium, boron. This is carbon. Right? And this is oxygen. This is your zigzag. Right now? That is how the zigzag appears. Actually, this zigzag trend is due to two reasons. The zigzag trend is due to two reasons. One is the atomic radius. The other reason is the existence of stable configurations. The existence of stable configurations. The zigzag is mainly due to that existence of stable configurations. The atomic radius suggests that ionization should increase gradually, and combine that thing with the existence of stable configurations, it is going to be a zigzag trend. So those are the two things matter: the atomic radius and the existence of stable configurations. One can say as to the atomic radius as the effectively charged metals, right? One can say this trend is due to the effectively charge as well as the existence of stable configurations, right now. Okay, that is the idea. So this is how the zigzag trend appears. Zigzag trend appears, right? So got the idea? Right. Let's write the stuff. Let's draw the stuff, right? So we can draw this one. So you can start drawing the drawing this thing, right? The idea is clear. You can think of drawing this one. So I'll teach you a very simple way of drawing this one. So not thinking of all the stuff, all the reasonings. I can give you a simple way of drawing this thing because in no time you should be able to draw this one. So I have just completed the reasons behind this zigzag trend. That is clear, no? Right. Then I'll teach you a very simple method, right, to quickly draw this one, right? So I have taken some time now to construct this one, right? Okay. So I'll erase this thing and give you a simple method to draw this one correctly because that is needed. So in 10 seconds, you should be able to draw this one, right? To answer the questions quickly in MCQs as well as in structured papers, right? Structured questions, these things will be asked, right? So let's see this, right? In no time how to draw this one. The idea is this, right? So when drawing this, right? Okay. Just go for this kind of thing, right? Just go for this kind of thing. And I'll erase this one. So when you are drawing also, you can use the same technique, right? When you are drawing this, you can use the same technique, right? So first of all, let's draw these ones, right? Right. So we can draw this one quickly, right? Like this. So when drawing this one, just draw like this. Okay. First draw a longer line. First draw a longer line. It's better to have a kind of 45 degrees angle. It's 45 degrees angle. Just draw a longer line. With some 45 degrees angle, just draw a longer line. Then with some 90-degree angle, just draw a shorter line, very short one, right? So 4 times of this thing may form this longer line. 4 times of this thing may form this longer line, right? Shorter line, right? Longer line, shorter line. Another longer line with 90 degrees angles. Angle always come with the 90-degree angle. Here also 90-degree. Another short line with 90-degree angle. Another longer line. Right? Longer line, shorter line, longer line, short line, longer line with 90-degree angles, right? Then on the first longer line, we are locating dots only on longer lines, right? Only on longer lines we are locating dots. Only on longer lines we are locating dots. We have to locate 8 dots or 8 elements here. So with the first longer line, only the corners are with elements. With next longer lines, corners as well as the center is with elements. Corners as well as center is with elements. So that is how we are supposed to come up with 8 elements, right? 8 elements in a row. Right now? Those are your 8 elements. So then you can come up with the names there, right? This is lithium, beryllium, boron, carbon, nitrogen. Then you have oxygen, fluorine and neon, right? So then you have beryllium, nitrogen, so as well as neon. Is it some stable configurations? Right? Is it some stable configurations? I write these things a bit higher, right? So then it is clear now. Heliums and 2s2 2p3. Here the heliums and 2s2 2p6. Right now. So those guys are with stable configurations, right? Right now, this one is with helium and 2s2 2p6. So it is very easy to draw this thing, right? Longer line, short line with 90 degrees angle, longer, shorter, longer, right? So with this method, if you have drawn this one, right, so that line is also there, right? So if you are to mark a line between matching the carbon and fluorine, you get that line. See? Which was supposed by the atomic radius. Right? This is so ionization trend. So by drawing like this, you clearly see that the beryllium's value is in between boron and carbons. The beryllium's value is in between boron and carbons. The oxygen's value is in between nitrogen and carbons. So you clearly see the thing by drawing like that. The nitrogen's value is in between fluorine and oxygen. Nitrogen value is in between fluorine and oxygen. So that should be clearly understood by drawing the ionization trend like that. Longer line, short line, longer line, short line, and longer line. Always you have to maintain 90-degree angles among lines, right? And at the first line only you have elements at the two corners. With the other two longer lines, right? You have elements at the corners as well as at the center, right? So this is how you're supposed to draw the zigzag trend, right? With all the knowledge, right now. So complete this one, right? Then we'll see what is appearing with the knot, and we have some spaces there, and we need to complete that thing as well, right? Okay. So first draw this one. So you can pause and draw this one, and then we can continue, right? Okay. Let's continue with the knot, right? It says, note says like this, right? Point number 1, it says, first ionization energy generally increases as we move across a period. First ionization energy generally increases, see? Generally increases as we go along a period. See, under that, just write in that space, just write this, right? Just write this to complete the knot. You can write in red color, just write in red color, just write atomic radius decrease. You can continue the statement. It says like that, first ionization energy generally increases as we move across a period as, write in red color, atomic radii decrease, as atomic radii decrease, atomic radii decrease. Within brackets you can write, within brackets just write Z effective increase, Z EFF increase, as atomic radii decrease, within brackets Z EFF increase, close the brackets, right? Okay, that is about the first ionization, why it increases normally, right? Okay. At the next line, just write. At the next line, just write. So. You can write the so in normal color. Come to red color again. Just write. Group 1 element shows the lowest I1. Group 1 element shows the lowest I1. You see, group 1 element shows the lowest I1, right? Shows the lowest I1 and next line, at the next line just write group 18 element shows the highest I1, Group 1 element shows the lowest I1 and group 18 element shows the highest I1. Okay, that is all for that space, right now. Okay. Next point. Right? It says the note. It says like this: the zigzag pattern in the trend is because of the existence of stable electronic configurations. The zigzag pattern is in the trend is because of the existence of stable configurations. It is said, right? Under that, they are saying A, group 18 element neon has the greatest I1. It is said group 18 element neon has the greatest I1. We'll write the reasonings behind that. Right? We'll write the reasonings behind that. Right? First write the configuration of neon. When we are supposed to write the reasonings for those trends, first come up with the electronic configuration. So first, as the first point, just write the configuration of the neon. Neon is equal to helium and 2s2 2p6. The shorthand notation of the condensed configuration is enough, right? Okay, just write this thing as the first point. Neon is equal to helium into 2s2 2p6, right? At the second point, just write removal of an electron from a completely filled subshell. Removal of an electron from a completely filled subshell. You can write within brackets, right? Ns2 np6. Removal of an electron from a completely filled subshell. Ns2 np6. Put a comma. Which is highly stable. Put a comma and write which is highly stable, comma, require more energy. So this is the Nobel gas configuration, right? This is Nobel gas configuration. You can write it as well if you need. You can write it that as well. Nobel gas configuration, right? Nobel configuration. So removing an electron from Nobel configuration is very hard. Require more energy, right? At the next line, just write so. Next line, just write so. Next point, you can write I1 for group 18 element. I1 for group 18 element. Within brackets neon, close brackets, is higher than is expected from the common trend. I1 for group 18 element is higher than is expected from the common trend. Right now, that is all about neon showing some greater value, or the neon is with the maximum value for I1 when considering elements in a single row, single period, right? That was the reason, because it's with a very stable configuration right now. Okay, next let's come up with the next point. B is considering about this, no? Point B is considering about this. It says like this, no? At the note, it says I1 for group 2 element beryllium is greater than that of group 3 element boron. I1 group 2 element beryllium is greater than that of group 2 element boron. That is what the note says, right? Let's write the reasonings. Let's write the reasonings for that, right? Always when writing reasonings, Lamai, you are expected to come up with electronic configurations because these are all governed by the electronic configuration. So first write the electronic configurations of those two things, right? For the beryllium as well as boron. So you can write the beryllium's configuration is helium and 2s2. The boron's configuration is helium and 2s2 2p1. Third drone, this is second drone. Right. Next point. Next point. You can write. First write this thing. Next point you can write. Electronic configuration of beryllium is a stable configuration. Electronic configuration of beryllium is a stable configuration with come to the red color and write Namai, come to red color and write completely filled S subshell. Completely filled S subshell. Stable electron configuration with completely filled S subshell. Right now? Okay. Next point. The next point. Third point. Just write. Right? Just write. So require more energy. Within brackets than expected. Close the brackets. To remove an electron from that stable configuration. So require more energy than expected, right? To remove an electron from that stable configuration. Right now? Okay. Next point. So when we comparing these things, right? First you need to come up with the electronic configuration. Then you have to say that why beryllium is showing some abnormally high value. Then you have to say why this guy is not showing such a higher value, right? Let's write that thing as well. Next point, right? Even though, right? Radius of boron is smaller than the radius of beryllium. You can write this. Even though radius of boron is smaller than radius of beryllium, comma, I1 for beryllium exceeds the I1 for beryllium Be exceeds the I1 of boron. So normally we expect if you are with a larger radius, we expect this thing to release electrons easily, no? Release electron easily than this one, no? We expect that thing, no? Right? Because when you are larger, right, you can release easily, as you have greater distance between the radius and the removed electron, right? But that is not what happens. Even though the radius is larger with the beryllium, right? Still you need great energy to release the electron. Why is that? Right? Because of the stable configuration, right? Within brackets just write. B is not with a boron, right? Boron is not with such a stable configuration. Like in beryllium. That is why Boron releases the electron easily than the beryllium. Right now? Okay. That is about this string. That is about this string. Let's discuss the same about this one. Next point. Next point is that nitrogen is showing a greater I1 value than the oxygen, even though nitrogen uses larger radius. Even though nitrogen's electron is seems like loosely bound to the nucleus, as it is a larger radius, still releasing electron from nitrogen is harder. That is due to this stable configuration. Let's discuss about that thing. Let's come up with the note. So that is the next point. Next part C. At this note, C says that nitrogen is with a greater I1 value than the oxygen. Let's come up with the reasons for that. First of all, Lamai, you need to come up with the electronic configuration for those. So nitrogen is with helium and 2s2, 2p3, and the oxygen is with helium and 2s2, 2p4. First, just write the electronic configuration. Those are the marking points, right? Okay, just write this. Right, just write this. Okay. Next, write electronic configuration of nitrogen is a somewhat stable configuration. Electronic configuration of nitrogen is a somewhat stable configuration with an come to the red color and write exactly half filled p subshell with an exactly half filled p subshell. See, exactly half filled p subshell with an exactly half filled p subshell. Right? Next point. So require more energy within brackets than expected close the brackets to remove an electron from that stable configuration. Right, no? From that stable configuration. Right. Next point, just write. Even though radius of nitrogen is larger than radius of oxygen, comma, I1 for nitrogen exceed the I1 of oxygen. I1 for nitrogen exceed the I1 of oxygen. Within brackets you can write oxygen is not with such a stable configuration. Like in nitrogen. That is the reason. Right? Oxygen is not with such a stable configuration like in nitrogen. So even though it is smaller, it will release the electron easily than the nitrogens. Right? That is the idea, because it is not with a stable configuration like in nitrogen. Close the brackets. Right now? Those are the major reasonings for these trends. So 3 reasons have been discussed with the stable configurations. That is about the beryllium boron situation, nitrogen oxygen situation, and neon is showing the greatest value. Right now? Okay. That is what you should know when we are concerning about the I1 values, the first ionization values, along a period. Right? When we are considering about first ionization values along a period, those are the things you should concern, and those are the reasonings to come up with a zigzag trend. Right? Main two reasons are the atomic radius, or one can say the affinity charge, and the second reason is all about the existence of stable compressions. Right now, those are the main two facts governing the zigzag trend. Right? That is all you should know about the period trend along a period, the ionic radius. Right. Okay. That is clear, no? Do you have any questions there? No. Clear, right? Okay. So then, let's discuss further on I1 trends. Let's discuss further on the ionization trends. Right? Let's have a quick break, Lamai. Right? Then we'll discuss further things you should know about the trends or variations with the ionization energies, right? The first ionization energies, right? So you can complete the note and we'll have a quick break and then start, right? Okay. Right, Lama. After the break, let's start. Okay, so we have just completed the discussion about the period trends, the ionization energy trend along a period, right? The zigzag trend. The reasons have been discussed, right? Now we are going to studying about the first 20 elements, how those things vary their first ionization energies, right? Okay, that is the major focus today. Now we are going to discuss, right? Okay, this is about the first 20 elements, how the ionization energies varies with those, right? So some very important things to be noted here. Let's see. So I have just drawn the diagram there, which is also appearing with your tute as well, right? This is the ionization energy trend for the first 20 elements, the first 20 elements. Let's see what are the major things we can grab from here, right? So when we are discussing about the ionization energies along a period, we had said that the group 1 element always with the lowest first ionization energy, and the group 18 element is with the greatest ionization energy when thinking of along a period. That was what we were discussed, right? But when it comes to the first 20 elements as well, you see the same thing but a bit extensively like this. So when it comes to first 20 elements, right, not only for a period but for when it comes to first 20 elements, when we are considering first 20 elements, the group ones are with the least values. The group ones are with the least values when it comes to first 20 elements. The group 1, the three group 1 elements shows the least values, the smallest values, right? So that is very important, not only for a group of elements, but when it comes to first 20 elements, yet again the group 1 shows the minimum values. So we can mark them, right? So I'll write it here. Most probably you can write these things and under the variation, right? So what we see is the I1, when it comes to I1 minimum values, right? So group 1s showing the least values, right? So when comparing group 1s as well, the largest group 1 element shows the minimum value. The largest group 1 element shows the minimum value. So larger UI, it is easy to release the electron. No? Larger UI, it is easy to release the electron. No? So because your electron is away from the nucleus, no? It is the smallest, right? Then you have the sodium, then you have the lithium. All other 17 elements are with greater values than these three group 1 elements, right? So group 1 elements comes up with the smallest I1 values, right? Group 1 elements. Right now, let's consider another one. That is a very important note to grab from this trend. The second one we are going to discuss. The maximum I1s. So, when we are discussing about the maximum value along a period for the I1, it was shown by the group 18 element. It was shown by the group 18 element. Why is that? Because the group 18 element is with the greatest stabilized electronic configuration. Group 18 element is with the most stable electronic configuration, right? So that those are not keen to get rid of that loosely bound electron, or one can say it is with the smallest radius. That is why it is not showing any kind of keenness towards releasing the electron. Anyway, so group 18 shown the greatest ionization when it comes to a period of elements, but when it comes to first 20 as well, they show the same. When regarding the first 20 elements, you see the group 1s are the ones with greatest values. Group 1s are the ones with greatest values, right? So let's go to that. Group 1s are the ones with greatest values. See? And we have a little bit of exception as well, right? We'll discuss about that exception as well, right? So group 1s are the ones with the greatest values, right? So that is the major thing to concern here. So yes, write that thing, right? So in your trend you can clearly see that, right? Sorry, group 18s are the ones with the greatest I1 values, right? And some exception is there. These are the group 18s, helium, neon, and the argon. And bit of exception is there. So see that as well. This is the exception. This is the exception. Fluorine. Even though it is not a group 18, still it is with some greater I1 value. Such kind of exceptions are appearing, right? The trend is that group 18 should show the greatest I1 values, but we have exception as well. So no worries, right? Such things may appear. So neither. We have a rule that group 18 should show the greatest values, right? But, right, sometimes some exception cases may appear. So those things are normal situations now, I know, right? So we have a rule that all the vehicles should go from the left hand side. That is the rule in Sri Lanka. But don't you see the exceptions? Don't you see some vehicles are going with the right hand side? The ambulances, they are capable of those. So exceptions are there, right? So when exception is appearing, you are not going to right, put away the rule, right? So 99% of the stuff will follow the rule, right? but here and there are some maybe some exceptions. So what we need to do is just take that into, we have to note that is it, right? Okay. So when it comes to I1 max values, the maximum values will be shown by group 18s with some exception. Fluorine is also there, right? And the smallest atom then should show the greatest I1. The smallest among the noble gases should show the greatest I1. That is very understood, right? Smaller you are, it is hard to release the electron because it is more closely, strongly bound to the nucleus as it is closer to the nucleus, right? So helium, neon, then we come up with the exception, the fluorine, exception, right? Right, then we have again the argon, right? All the other guys are less than that, other 16, the 16 element, right? This is about trend. This is about group 18 noble gases, and there we have exception as well, right? This is VIP situation, right? VIP. VIPs can go from any side of the road. That is normal, right? In Sri Lanka, right? Okay. So that is the idea. Right. So these two things should be noted, right? When it comes to these trends. Few more discuss. Right? So it is better to know the position of hydrogen as well. In some papers, they have been asked about that thing. It's better to know the position of hydrogen as well. So position of hydrogen. So hydrogen is here. Actually, the hydrogen is in between the N and O, in between the no. Hydrogen is in between the N and O. So keep that in mind as well. The hydrogen is between the right? That is another thing you should know to have come up with a better result, right? So what else you should know about the first 20 variation? Another thing you should know is actual amine, right? When it comes first 20, right? Another thing we can note is actually the variation of first ionization energy of diagonal related atoms. Let's discuss about that thing as well. Diagonally related atoms. Diagonal related atoms. Right? So, what is the diagonal relationship? In chemistry? Right? We see like this, no? This is applied for the P block elements, right? Boron, carbon, nitrogen, oxygen, fluorine, those things are there, no? Right? The aluminium, silicon, phosphorus, sulfur, chlorine. So these values are given for these, right? I'll just write 800, the values given in resource book. 1420, 1314 and 1680. No need to memorize these values. What we are supposed is actually to come up with some special points here. 876, 12999 and right. In chemistry diagonal relationship, right? Diagonal relationship means this. So normally in mathematics, right? Mathematics, these are referred to as diagonals, no? These are referred to as diagonals, no? In chemistry, only this is referred to as a diagonal, right? In diagonal relationships, we are considering only about this in chemistry, right? Not about this, right? This is diagonal relationship in chemistry. So these are considered as diagonal related atoms. The boron and silicon are considered as diagonal related atoms. Carbon and phosphorus. Carbon and phosphorus are considered as diagonal related atoms. The oxygen and chlorine are considered as diagonal related atoms. For ionization trains, we are not going to relate the nitrogen lamine. We're not going to relate the nitrogen because nitrogen is showing some abnormally high value. Nitrogen is showing some abnormally high value, no? So we are not considering that thing. Other than that, these can be considered as diagonal related atoms. So we can see some trend here. We can see some trend here. Right? What is trend? So diagonal related atoms are with closely related values. See, 800, 876, 886, closely related values. 1086, 1200, yeah, somewhat closely related, right? See, closely related values. So that is what we need to know, right? Diagonal related value, atoms are with closely related values. Diagonally related atoms in P block are with closely related values. The values are close. See? But note that, the larger one is with out of those two diagonal related atoms, the larger one is with a smaller I1. The larger you are, it is easy to release the electron, right? But with them, there is more precisely. Large atom is with a slightly lower I1. So these things should be known to answer quality question, right? That is the diagonal relationship. That is the diagonal relationship, right? Okay, those things can be grabbed from this kind of relationship, right? No? Okay, just complete the note. Right, let's discuss a question. Right, with these things, why we need to study these ones. Let's come up with a good question which actually appears with the papers, right? Then you can understand why we had went for this kind of extreme, right? Okay, let's discuss a question here, right? Let's try to come up with an answer for your question appearing at the next page, right? At the study questions, there's a question like this. You were expected to locate these guys. You were expected to locate these guys, right? You were expected to locate these guys. Right? So let's have some phosphorus as well. you are expected to locate these guys in the increasing order of 3, 4, 5, 6, 3, 4, 5. In the increasing of I1. First ionization energy. Let's see. The first ionization energy. I leave this thing, right? Let's see how to solve this one, this kind of question. Now first think of the minimum and maximums. First think of the minimum and maximums, right? So you can't just solve this kind of question by just knowing the zigzag. Just knowing zigzag is not enough to solve this kind of question, because all of these elements are not belongs to the same row. All of these elements are not belongs to the same period, right? So not only the zigzag is enough. Only the zigzag is not enough to complete solve for this thing, right? So we have to use these things, right? So minimum values and maximum values are needed. So these comes as minimums. These comes as minimums, I1 minimums, right? The group ones comes as I1 minimums. So those are at here. The larger out of those two will have a smaller I1 value, larger UI, it is easy to release the electron, less energy needed, right? So sodium is with a smaller I1 compared to lithium. The minimum values. I1 means I located these two with the knowledge of I1 minimum values. Right? Do we have anyone with maximum I1s? No, we don't have any one with maximum I1s, so we can't locate these four then with the using of maximums, right? Let's come up with the next ones, right? Third, so beryllium, boron, nitrogen, phosphorus. Beryllium, boron, nitrogen, phosphorus. Then when regarding those, right? Beryllium, boron, nitrogen, phosphorus, right? When regarding beryllium, boron, nitrogen, phosphorus, actually these three comes with the same row elements, same period elements. So first concern those. If you don't have any way to locate the phosphorus, then only you prefer the diagonal relationship, right? First come up with these. So the same period guys comes up with the zigzag. Comes up with the zigzag. So lithium, beryllium is here, boron is here, nitrogen is here. So with the zigzag, right, you can locate the beryllium, boron, nitrogen. So nitrogen is having the greatest, beryllium and boron is with smaller value. So beryllium is this, so boron is the smallest, then the beryllium, then nitrogen. That is about the same period, guys. So that is how we solve a question, right? First come up with the minimum and maximums, then look for the elements at the same period to come up with the zigzag. Then we have to locate remainings with the use of diagonal relationship. So this could be used. You can use the diagonal relationship to locate this. Diagonal relationship says, right? Diagonal relationship says the phosphorus is diagonally related to the second row. This is second row. This third row. phosphorus is diagonally related to the second row element carbon. So phosphorus value is closer to the carbons. It is a bit smaller than the carbons, anyway it is closer to the carbons. So we can locate phosphorus in the position of carbon. We can locate the phosphorus in the position of carbon. This is how we use the diagonal relationship. We can locate the phosphorus in the position of carbon. This is how we bring the phosphorus to the second row using diagonal relationship. So phosphorus should appear in between beryllium and nitrogen. Phosphorus should appear in between beryllium and nitrogen. So phosphorus should appear here. Right? Phosphorus should appear here. Yes, one can say definitely phosphorus is having a lower ionization energy than the nitrogen because phosphorus is larger. With the same group, phosphorus is larger, so phosphorus should have a lower ionization energy. One can see that. But the thing here is, right, just using that knowledge, we can't say whether the phosphorus appears here, here or here, no? Even here as well as here. Right, those are positions where you come up with lower values than the nitrogens. So that is a problem. So correctly locate the phosphorus, we need the diagonal relationship. Right? It says phosphorus can replace the carbon in your second row according to diagonal relationship. So now the trend is actually, right, boron is here, beryllium is here, and nitrogen is here, and phosphorus comes in between beryllium and nitrogen according to diagonal relationship. Right now, that is how we are supposed to solve this kind of question. Right now, so you can just do the workings and complete that question. Right? Yes, this thing. Right now, okay, let's come up with the last topic, the last thing we should know about the ionization trends. We have learned all about the first ionization trends, right? Now we are going to discuss a bit about the second ionization trends as well. Even though that second ionizations are not appearing in your resource book, they have been questioned in your last few A-level papers. You can see the last year's paper, right? Right, so you will see that the second ionization is questioned, the trends are questioned, right? So let's discuss about that thing as well, because they will ask questions on second ionization even though it is not at the resource book. See that, right? Okay, let's quickly discuss about the second ionization as well, right? Let's come to the next topic, right? Okay, Lama, let's discuss the second ionization energies, right, quickly, as we are running out of time, right? So second ionization energy. Basically, we are considering about a longer period, right? Okay. What is meant by second ionization energy? The I2 means you are supposed to release an electron to produce the 2 plus gaseous atom. Sorry, 2 plus gaseous ion. You are supposed to release an electron to produce the 2 plus gaseous ion, right? So that the electron should be removed from gaseous plus 1. To conserve the charges, this should be plus 1. So second ionization means, right, you are supposed to you're supposed to produce the second ion, the +2 ion, by releasing just one electron. That means that electron should be released from +1 gaseous ion, right? This is second ionization. So let's discuss about the period trend of second ionization energies. Right? Is I2 in kilojoules mole is atomic number. Right now? Okay. So let's come up with the trend. The idea is same, Laman. The idea is same. Right? First think of the one which carries the least second ionization. Let's think of the one which carries the least I2 minimum value. So the electron will be released easily. Electron will be released much easily if that atom attains a noble gas configuration, the most stable configuration, by releasing the electron. If you attain the most stable noble gas configuration by releasing the electron, then you will release the electron very easily. You are very keen to do so. Why? Because you can get the greatest stability by achieving the noble gas configuration, right? So the minimum, the least I1 value, I2 value, the I2 values with the element which attains the noble gas configuration by releasing the second electron. By releasing the second electron. Second ionization means, right, releasing the second electron, right? So the element which attains noble gas configuration by releasing the second electron, get rid of that electron much easily. Very minimum energy is sufficient to release that electron from that element. So what is that element? That should be the group 2 element. That should be the group 2 element. I1 minimum is actually the element achieves the noble configuration by releasing the second electron. By releasing the second electron. Right? So if you are, so that should be the, actually that should be the, what is that? That is the group 2 element. It is a group 2 element. By releasing second electron, so the group 2 elements are with 2 electrons at its valence shell. So releasing 2 electrons means you are coming up with the noble gas configuration of the earlier right shell. So that is the idea. So if you are regarding to third row elements, it should be the magnesium. It should be the magnesium. It should be the magnesium. So magnesium shows the least I2 when it comes to group 2 elements, right? So the trend is zigzag, but the trend should start with magnesium. That is the idea. The least I2 should be shown by magnesium. Right? Magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, fluorine. Right? So the least value I2 min with the group 2 element. Right now? That is the idea. So we should come up with the maximum I2. I2 max. I2 max. That is when you are supposed to release the electron from a noble gas configuration. If you are releasing the electron from the noble gas configuration, then you are not keen to release that electron because you are with the most stable configuration, so that you are not keen to get rid of that configuration. So the one with the noble gas configuration shows the greatest I1, I2, greatest I2, right? So I2 max is coming from the element with the noble gas configuration, right? So this with the element which loses the noble configuration. By releasing the second electron. That is what? That is actually group 1 element. After releasing the first electron, the group 1 element achieves the noble gas configuration. The second electron is going to be removed by that noble gas configuration, right? So the second electron is removed from the noble gas configuration for the group 1. So group 1 guys are the ones which is with the greatest I2. So that is like this. That is sodium in this case. The greatest I2. So just remember the smallest I2. Then you can continue this side as normal. I'm not going to mark this one because the next element, this is argon. Next element belongs to next group, no, the potassium. So I just consider only the third two elements. So this is the I2 trend, right now. So just complete this one now. Right now, okay. With this, we'll complete the today's session. Right, we can complete the today's session with this one. Right, then at the next class, we'll study about the next period trend. Most probably, we will going to study about the electronegativity at the next class. Right, that's it for today. Right, thank you, and see you next week. Goodbye then.